I'll have to find, he's probably somewhere else now.
All right. Our final talk for this morning is Mel Nathanson, and he'll talk about sunsets of lattice board.
Thank you. So I want to first of all wish Krishna a belated happy birthday, and I want to thank the organizers for the invitation to talk here, even though I have absolutely nothing whatsoever to say about prime numbers or Q series or partition identities. I'm going to talk about some problems in combinatorial and additive number theory. And as you see, I'm using slides. So the first time I ever did this was at Ron Brown's birthday conference last summer. And I would put up a slide and look at it and say, that's interesting. And put up another slide, and that's not so. And I thought I was looking at someone else's talk. So I'm not sure how this goes. So I have to give an overview. So I start with some stupid anecdote about how the inefficiency of the Soviet railroad system created additive combinatorics. Then there's some notions I need to introduce, some sets, different sets, approximate groups, asymptotic approximate groups. There's a main theorem that says that everything that's finite and abelian is eventually an approximate group, and then some open problems that there are mainly two left. So in additive number theory, we add stuff. So you take, let's say, an additive abelian group, some subsets, A1 up to A8, and you form this subset. So that's like the primitive object, and if all the different sets you pick are the same, you're looking at the H-fold sum. And if you take the union of all the H-fold sums, you have an additive semigroup. And we especially like just adding two things, the two-fold sum set A plus A, and the difference set A minus A. So sums and differences are nice. If you add two things, A1 plus A2, you can also add A2 plus A1, and you notice they're the same, right? But if you take two elements that are different and you subtract them, you get something non-zero, A1 minus A2. And if you subtract them the other way, A2 minus A1, you get a different element. So even though, because A1 plus A2 equals A2 plus A1, but A1 minus A2 is not A2 minus A1, you might suspect that the sum set always has no more elements, never has more elements than the different set. This inequality at the bottom. And you can perform the following experiment, which will work 100% of the time, or let's say in probability 1. Here I just picked a random set when I was writing up these notes, and you add it up, and you get these numbers, and you look at the different set, and it seems like there are 10 elements in the sum set and 13 elements in the different set, and 10 is less than 13. That's what you expect. Or you take another example. This is integers from 0 to 14, so the sums are going to be between 0 and 28. And if you add them up, I wrote down what you get. You get everything except 120 and 27, so you have 26 elements. And if you look at the different set, you actually just have 25, and there's a theorem, 26 is bigger than 25. So this is really an unusual set. I call these MSTE sets, because I have no originality about these things. More sums than differences. And so the first example was actually, I forget who found it. It was published, I think, in the Journal of Combinatorial Theory. It was called a counterexample to the conjecture of Conway. Conway allegedly said that the sum set should never be bigger than the different set, and this was a counterexample. And I asked Conway one day, I said, no, I didn't make that conjecture. In fact, I did find a counterexample, but not with integers, so it's more complicated. But these are interesting, and I'll come back to them a little bit later if I have a chance. But I'm interested in what's results originally to Grigori-Freimach, which has to do with the size of some sets. So this is an ancient theorem. If you take a set of k integers and you add it to itself, it has at least two k minus 1 elements and no more than k squared plus k over 2 elements. And what we call a direct theorem in additive number theory, it's a theorem that says if you know something about the structure of a set, then say something about the sum set. So if you have an arithmetic progression of length k, the sum set is as small as possible. That's a direct theorem. And the inverse theorem, which is also ancient, says if you have a set of integers whose sum set is as small as possible, it must be an arithmetic progression. Now, an arithmetic progression, this plus this plus this. So you can translate it so the smallest term is 0, so it's just multiples of something d, and you can divide by d. You haven't changed anything. So essentially, you're looking at a set of consecutive integers. And a set of consecutive integers is like you take an interval on the line, it's the integers inside the set. So this convex set, which is an interval, when you have this sum set of minimal size, it's the set of integer points, lattice points, are in this convex set. That's sort of the idea of this theorem. And let's see how this goes. So Feynman knew this, and so again, we say that a set is small if its sum set is linear in the size, right? If a set is k elements, the sum set is between k and k squared. So if it's constant times k, we say it's small, the sum set is small. And Feynman's first theorem was, suppose you have a set whose sum is not as small as possible. It's not 2k minus 1, it's 2k, just a little bit bigger. And his conclusion is, there's an arithmetic progression of length k plus 1, and you have k elements of that. You leave one out. So it's almost an arithmetic progression, but there's like this one little hole in it. Now, this led to the whole subject of additive combinatorics. And how did this come about? So Feynman told me this story. He told me variants of the story, so I picked the one I liked the best. And I had similar experiences. You're in the Soviet Union, you're waiting for a train, and it doesn't come. And eventually a train comes, but they don't let you on it. So you have to wait. So you can spend the whole night at the station waiting to get on a train. And this is what happened to Feynman. He was stuck at a train station somewhere waiting for the train. And he started thinking about the fact that, what happens if you have a set whose sum set isn't as small as possible, just a little bit bigger. And he came to this idea and a lot of other ideas. And the big theorem, Feynman's inverse theorem, says if you pick a number c, and you have a set of k integers, and the sum set has at most c times k elements, those linear in k, depending on this constant c, then your set really is like the set of lattice points inside some convex body, some parallel pipette. So, if you think of it, you take a parallel pipette, you add it to itself, it doesn't get too much bigger. And if you look at the lattice points, you add them, they don't get too much bigger. And that's the canonical case. That's the only way a set can have a small sum set. So this is quick and easy form of Feynman's theorem. The structure of a set, so this is an inverse theorem. If you know the sum set is linear in the size of the set, it has to look like most lattice points inside some parallel pipette.
Yeah, but how should we think of this as integers?
Sorry? Well, so,
The projection?
yeah, so you can project the parallel pipette onto the line and you have what's called a multi-dimensional arithmetic progression. But, so maybe I should put isomorphic in quotation marks, but there's a precise notion of isomorphism, which is now called a Feynman isomorphism, which just establishes this kind of projection. But there's no difference between lattice points on a line and lattice points in a box. So, of course, this has to do really with integers or maybe with additive abelian things. And people thought about non-abelian versions of this. And so the idea, so there's this notion of an approximate group, which is really a kind of way to generalize Feynman's theorem. So if you have a box and you double the size, you can, with a convex set, addition and dilation are the same thing, right? If you take a convex set and you dilate it by an integer h, it's exactly the same as adding a set to itself h times. And the sum set really is just like, it's covered by a small number of translates of the original box. So you take a box and you double it, and a small number of translations of the box covers the box. So that's this notion of an approximate group. So you have a set A, and you call it an RL approximate group. I should just have let R equal 2. But means if you take the R-fold sum set is contained in X plus A. X is a small set, L elements. X plus A really means L translates of the set A. So the sum set is contained in a small number of translates. And if you have such a phenomenon, such a thing, the sum set really is linear in the size of the set. So this notion, I think, was introduced by Turing Tao, but he only considered R equal 2, and he only considered finite sets, and he wanted his sets to contain the identity and to be symmetric in some sense, none of which is all too complicated for me. So we just take a set A. It doesn't have to be symmetric, doesn't have to be finite, just a set A. And so if a set A has a sum set covered by a small number of translates, it's an approximate group. But if, your random set is not going to be an approximate group. But sometimes nature is nice, right? And if you sort of smooth out your set, in this case, since we're doing things by addition, you add the set to itself enough times, it might be if you add the set to itself enough times, some fixed number of times, you end up with something which is an approximate group. So I call that an asymptotic approximate group. This just means that you have some set A, which is an asymptotic approximate group. If you add it to itself, h naught times or anything more than h naught times, every sum set from a certain point on is an approximate group. So that's the sort of the asymptotics. The set itself is not an asymptotic, not an approximate group, but eventually it is. So now it's not the case in the real world, which is non-abelian, that everything eventually, and then you replace addition by multiplication. It's not the case in the real world that everything is eventually an approximate group. And if you want to find a counterexample, you try the standard counterexample for everything in group theory, which is you take a free group on 2 generators, and you take your set to be the 2 generators. And no matter how many times you multiply this by itself, you will never get an approximate group. So in the non-abelian world, not everything becomes an approximate group. Now, but in my world, the integers, in fact, every non-empty finite set of integers is an asymptotic approximate group. So, for example, if you take R equal 2, this means what? If you take any set of integers, add it to itself enough times, the two-fold sum is always covered by 3 translates of the set. That's a 2-3 approximate group. And the proof really depends on sort of a basic theorem in additive number theory, which I like a lot, but it's way too complicated. So it's easy. If I had a couple of minutes, it really is easy, but you have to like.
And it was on the T-shirt for your birthday.
Yes, it was. Okay. So, all right. So integers are good. Every finite set of integers is an asymptotic. I want to look at other things. In geometry, if you take a finite set of points and the convex hull is called a polytope. So let's see. So forget vector space. This is Rn. Take a finite set of vectors in Rn and take the polytope, the convex hull. So every polytope is an approximate group. And but for my purposes later, I need a more precise version of this. So I have this set A, and I can look at all the sum sets. And the union of all the sum sets is this semigroup, which is this S of A. So when I say that this polytope is an approximate group, it means what? It means if you take the R-fold sum of the polytope, or if you dilate it by this factor of R, it's covered by a finite number of translates of the original polytope. And I want to control the translates. And it would be nice if the translates were all in the semigroup generated by these sets that create the polytope. But that doesn't quite happen. So the R-fold sum is contained in this set 1 over k minus 1 times xr plus k. So k is the polytope. xr is some elements in this semigroup, but I have to put in some denominators. k minus 1. So they're not too far off, but it's a fixed factor. They're almost like translates by elements of the symmetry. And, but the sort of the takeaway is polytopes are approximate groups. They're not finite. And to prove this, I use a beautiful theorem of Hovansky. Let me just sort of forget what's on the slide. I'll tell you what the theorem says. You take a set of lattice points in Ra, and let's say that as a group they generate the whole lattice. So you have the set of lattice points, and then you take the lattice polytope they generated, and you dilate the lattice polytope by a factor h, and it will contain a lot of lattice points. Some of them will actually be h-fold sums of the generating lattice points, but not all of them. There's no reason why they should all be. But Hovansky's theorem says that if you dilate your polytope, there is a sort of a boundary layer. There's a sort of a fixed distance, and every lattice point, this fixed distance away from the boundary is actually in the h-fold sum of lattice points. It's not a hard theorem to prove. It's a hard theorem to imagine. It's actually, for him, it's a lemon. His paper is little papers. But he's trying to do something else. But this is really a very nice result. And from that, we get something too technical to talk about. But so then we get to the serious thing, which is, just as every set of integers is an approximate group, every set of lattice points, every finite set of integers is an asymptotic approximate group. Every finite set of lattice points in Euclidean space is an asymptotic approximate group. And then you put that together with whatever is the structure theorem for finitely generated abelian groups, which is every abelian group is essentially the lattice plus a finite piece, and finite abelian things are approximate groups. And this says the lattices are. So you get the main result, which is every non-empty finite subset of an abelian group is an asymptotic approximate group. So that's what I said in the beginning. Everything abelian is an asymptotic approximate group. But not everything is. Right, non-abelian things are not. So, so that brings us to problems. So our first obvious problem is, when does a non-abelian group have, or what non-abelian groups might have the property that a finite subset is an approximate group or an asymptotic approximate group. So just as the free group of rank 2 is your go-to group for a counterexample, your go-to group for a non-abelian thing, which is nice, is the Heisenberg group. So you look at these 3x3 matrices, just like that, integer entries in the upper top half. It's nilpotent of level 2 or step 2, and so it's as close to abelian as you can get if you're not abelian. So everyone loves the Heisenberg group, and it's just an interesting question, which I don't know the answer to, whether finite subsets of the Heisenberg group are asymptotic groups, and because you expect things to be motivated and not motivated. I don't know what the word is. In the same equivalence class as Gromov's theorem, you might expect that at least finitely generated irrevocable groups have this asymptotic approximate property. That's just a question I have no answer to. If nothing else. One or two other problems. I gave an example at the very beginning of these sets with more sums than differences, and they're really rather mysterious. There are some systematic constructions. There are there was a big additive combinatorics meeting in Montreal a few years ago, and I said something like almost the probability of one a random set is not a more sums than differences set. They're really rare. And then two theorems were published on this subject. One said that the probability one, a set does not have more sums than differences. And the other said that with probability, 0.9873, the same answer. And both theorems are true, just how you put probability measures on collections of finite sets. So you have Steve Miller and company at Williams College, and Kevin O'Brien and his collaborator at Vancouver. So whether it's 100% or 99 point something percent, really it's sort of how you count. But basically, if you pick a set at random, it will not have more sums than differences. Rouge, however, recently looked at an old paper of Haidt. And he gave a talk on this at this meeting in Graz. And he said when he was a graduate student, Erdős gave him a preprint of Haidt's paper and told him it was really interesting. And 40 years later, he looked at it, and it really was, it really was interesting. Also, the paper was published in Mathematica, and I checked on MathSciNet. There were essentially no references to it in the last 40 years. And Haidt had a weaker version, and Rouge had a much stronger version. Haidt was interested in a problem in measure theory, constructing measurable sets with some properties, but he needed this congruence result. And so part of Rouge's paper is more or less a construction that you can find. So instead of more sums than differences, it's more differences than multiple sums. So you can find the set A, mod Q, where the difference set is the whole ring of congruence classes mod Q, but the sum set is less than epsilon Q. So for any epsilon, for any H, you can find a set A of residues mod Q, where the difference set is everything and the H-fold sum set is small. And the way you do this is just like a iterated use of the Chinese remainder theorem, putting together products of congruence classes. It would be actually interesting, this is somewhat maybe a technical problem, but to show that for every large prime P, you can actually construct a set of residue classes mod P that whose difference set is everything and whose H-fold sum set is very small.
So you have an existence proof on it? You have no constructor?
No, for Q, it is a kind of a construction, but what it produces is an integer Q, which is a product of some vast number of primes. There's also a general theorem that says that this is true even for just a sufficiently large prime. But for that there's not a constructive proof. And so Rouge actually also in January of this year put a preprint up on Archive on exactly the subject. This is actually, I just mentioned this because it's related. It's very interesting. It's complicated, but the difference set and the sum set, you can have a smaller difference set than sum set or a smaller sum set than difference set, but the differences can't be too big. And so this is an old inequality of Feynman and Pigayev, which bounds the sum set in terms of the difference set and the difference set in terms of the sum set. And in Rouge's paper, which I highly recommend, it ends with the following problem, which is, on the one hand, you might say a kind of idiosyncratic problem in number theory, but for me it is a perfect problem in the kind of number theory that I like, which is, so this is Rouge's question, is it true that for every finite set of integers, if you look at the fourfold sum, it cannot be bigger than the square of the difference set? Thank you very much. Oh.
Questions?
Yeah, just what was the date on the Khovansky paper?
Excuse me?
When was Khovansky published?
Khovansky.
Which Khovansky?
Askold Khovansky, A.G. Khovansky, a student of Arnold. The paper was in Delphi Journal, Functional Analysis and Its Applications, in the 1990s, 94, 5, 6, A2.
Any other questions? No, thank the speaker again.
Cindy Garland was supposed to make an announcement at this point, but anyway, she's not here, so I will speak on her behalf. So, when these talks were going on, we noticed a few people standing in the back, although there were some empty seats here, they didn't obviously want to disturb anyone who was coming in. But for this movie, we expect this hall to be packed, and we don't want the fire marshal complaining that there are people standing. So please do come and fill all the seats, and it will be packed to capacity because the spouses of participants also will be coming, and so we expect the hall to be